Hi everyone, this is our final video in the series of videos about zeros of a polynomial function. In this video, we're going to learn two more theorems about zeros of a polynomial function. The first one is called the conjugate pairs theorem, and basically it says that non-real zeros of a polynomial function always occur in conjugate pairs. Well, we talked about how zeros of a polynomial function can be either real or non-real numbers. Well, when function has the non-real zeros, they will always come in pairs. They will never occur alone. Let me give you examples of conjugate pairs. They're also called complex conjugates. Well, here's one non-real number, 5 minus 7i. And if you remember, this is a standard form of a complex number, real part and the imaginary part that contains the imaginary unit I. So, for the complex number 5 minus 7i, the conjugate is 5 plus 7i. So the idea is pretty simple. The complex conjugates have opposite signs in front of the imaginary parts, and everything else is the same. Here's another example. If one complex number is negative 1/2 minus I squared of 2, then its conjugate is negative 1/2 plus I squared of 2. So again, notice that the only difference is the sign in front of the imaginary part. And here's the last example. This is the complex number that does not have a real part, just the imaginary part. 3i and negative 3i. These are the complex conjugates. And now let's reread this theorem again. Non-real zeros, in other words, this kind of zeros, of a polynomial function always occur in conjugate pairs. So basically, if 5 minus 7i is one of the zeros of a function, automatically, or I should say by this theorem, we know that 5 plus 7i is also going to be 0 of that function. Let's practice this concept by doing the following example. It says find a third-degree polynomial f of x with integer coefficients and with zeros of 2 plus I and 4 over 3. Okay, so we need to find a third-degree polynomial. Well, if it's a third-degree polynomial, then how many zeros does it have? It means that it has 3 zeros, right? We already know that 4 over 3 is one of the zeros. That's the given one. 2 plus I is another zero. It's also given. But what is the third zero? Well, based on the conjugate zeros theorem, the third zero will be the conjugate of this one. This kind of non-real zero cannot occur alone. It always comes in a conjugate pair. So what is that zero? It's 2 minus I. Remember, we simply switch the sign in front of the imaginary part. Okay, so now we know all 3 zeros, but how do we find the function itself? Well, we're going to use the fact that if it's a 3-degree polynomial, then it can be written in a factored form, where each factor contains x minus, and then 0 of the function, minus 4 over 3, x minus second 0, 2 plus I, and I'm using the parentheses here because this non-real zero has 2 terms, right? And then the third factor is x minus 2 minus I. And there's also going to be a leading coefficient that we're going to figure out later. For now, I'll just say a sub n. Well, we're not going to leave the function in this form. We're going to multiply everything out. First, I'm going to start by clearing the parentheses inside these 2 expressions. Next, I'm going to start multiplying out the expressions. So pick any 2 and multiply them first, and then multiply everything else. It doesn't matter which 2 you're going to pick. However, I prefer starting with expressions involving imaginary unit, so I can get rid of it. And you'll see how it's going to disappear in the process. Now, this means that I will have to multiply expression involving 3 terms by another expression involving 3 terms. So ID is very similar to foiling. We just have to adjust it to this number of terms. So first I'm going to take x and multiply it by everything within the second expression. Then I'm going to take negative 2 and multiply it again by everything inside the second expression. And then I'm going to take negative I and also multiply it by all terms within the second expression, like that. I just have to be careful not to make any typos. Okay, so try to follow me. It's going to be x squared minus 2x plus xi minus 2x plus 4 minus 2i minus I times x plus 2i, and then minus I squared. I times I is I squared. Now, what can we simplify right away? I noticed that negative 2i and positive 2i can be cancelled, and positive xi and negative ix, these are also like terms that cancel each other out. What else I'd like to note here? The last term is I squared. And let me remind you that I squared is the same as negative 1. So it means that I squared I will replace by negative 1. Here I will end up with two negative signs, which I need to remember to replace with a plus. Okay, so I'll have x squared. Then I can combine negative 2x and negative 2x, it's minus 4x. And then I have positive 4 or plus 4, and here I'll have plus 1. So 4 plus 1 is 5, so plus 5. Okay, so now I have to multiply these two expressions. I'll take x and multiply it by everything inside the second expression. And then I'm going to take negative 4 over 3 and multiply it by each term inside the second expression as well. So that will give me x cubed minus 4x squared plus 5x minus 4 over 3x squared minus 16 over 3x minus 20 over 3. And even though I can combine like terms here, at this point, to avoid working with fractions, I'm going to think about the leading coefficient and apply it. What should be the leading coefficient? Well, remember how in the problem it says that we need to find a third-degree polynomial with integer coefficients. That means that they're not fractions. And here, obviously, I do have fractions. So basically, we have different choices for a sub n in this case. But no matter what we choose, it should be such number that once we multiply all terms by that number, fractions are cleared. So obviously, this leading coefficient should be a factor of 3. So we can choose from numbers 3, 9, 12, etc. Well, let's go with the lowest number to make it easier to multiply. Let's use 3. So if I choose 3 for the leading coefficient, and if I distribute it, I'll obtain 3x cubed minus 12x squared plus 15x minus 4x squared minus 16x minus 20. And now I can easily combine like terms. So the polynomial function f of x that we found is 3x cubed minus 16x squared minus x minus 20. That's the final answer. And the last theorem that we're going to talk about is called the intermediate value theorem. It says that if f of x is a polynomial function with only real coefficients, and if for real numbers a and b, the values f of a and f of b are opposite in sign, then there exists at least one real zero between a and b. Let me illustrate what it says here, and most likely you will realize that it's a pretty simple idea. Let's consider this arbitrary polynomial function f of x. And here are the chosen numbers a and b and the corresponding function values. So x value a corresponds to a point on the graph such that its y value is the same as the function value. Remember, we practiced that when we learned about functions. If you need to refresh this idea, please re-watch the video on the function notation. And now this is the x value b. Here's the corresponding point on the graph, which means that the y-coordinate of that point is the same as the function value. And now what can we say about those two function values? The first one, f of a, is located below the x-axis. So that means that it's a negative function value. And the function value f of b is located above the x-axis. It means it's positive. And now let's reread this part of the theorem. It says that if for real numbers a and b, the values f of a and f of b are opposite in sign, and that's what we observe here, negative versus positive, then there exists at least one real zero between a and b. So between a and b, there should be at least one real zero function. And here it is on this picture. Remember, zeros of a function are the same as the x-intercepts. Well, because function value at that point is 0. And now hopefully altogether this makes sense. So basically, if f of a and f of b are opposite in sign, it means one point will be below the x-axis and one point will be above the x-axis. And since graph of a polynomial function is continuous, there are no gaps. It means that those 2 points have to be connected, and the line cannot help but to cross the x-axis. Now, in this picture, the line crosses the x-axis only once, But it's also possible that before a line connects those 2 points, it makes a few turning points. So that's why in the theorem it says that there exists at least one real zero, meaning that there could be more than one. And let's practice applying this theorem by doing the following pretty straightforward example. It says, show that the given polynomial function has the real zero between 2 and 3. Now, to show that, we have to find p of 2, we have to find p of 3, and to confirm that these function values are opposite in sign. One is positive and one is negative. Let's see. To find p of 2, I need to plug 2 into the function for every x. So it's negative 2 cubed minus 2 squared plus 5 times 2 plus 5. Please keep in mind that when we have negative sign in the power, if no parentheses are written, it means that power does not apply to the sign. So power only applies to the number. We're going to cube 2 and then attach that negative sign. We're going to square 2 and then again attach that negative sign. Negative 8 minus 4 plus 10 plus 5. This is 3. And then to find p of 3, we're going to plug in 3 into the function. So it's negative 27 minus 9 plus 15 plus 5. That is negative 16. Now, because p of 2 has a positive sign and then p of 3 has a negative sign, in other words, point at the graph of this function at x equals 2 lies above the x-axis, and point at x equals 3 on that graph lies below the x-axis. So in order for those 2 points to connect, line has to cross the x-axis at least once, can be more than once. Okay, so here I typed up the answer. Because function values differ in sign, the intermediate value theorem tells us that there should be real zero between 2 and 3, but I also would like to add that, well, the common sense also tells us that. And at the end, I would like to make a warning about the interpretation of the intermediate value theorem. If we know that f of a and f of b are not opposite in sign, this does not necessarily mean that there is no zero between a and b. Let me illustrate that. Here's an example where at a, the function value is negative, and at b, the function value is negative. However, we can clearly see 2 zeros between a and b. So that means that the intermediate value theorem should be used and apply exactly the way it's written. If function values differ in sign, well, this guarantees that there will be at least one real zero. And for all other cases, the intermediate value theorem does not provide any conclusions. Okay, so with this theorem, we finish our series about zeros of a polynomial function.